Now let's continue our inquiry into scaling relations for galaxies. I already introduced the fundamental plane of elliptical galaxies. It is a set of bivariate correlations between many of their different properties, always unified in a way that any one of them can be expressed as a logarithmic combination of two others. And so usually it's expressed as scaling relation between radius, surface brightness, and velocity dispersion, because that's a very useful way of taking it, but it could be any other. And what's shown here is the plot of what it looks like in almost face-on, where you don't see much correlation at all, and essentially edge-on, where the only thickness is due to the measurement errors. I mentioned that you can use different quantities. Indeed, you can. So, for example, you can substitute luminosity for radius, and so this you can think of as the improved version of Talley-Fisher relation, but it's really fundamental plane projection slightly differently. And you can also use galaxy metallicity expressed as strengths of indices like magnesium or iron, which implies a couple interesting things. That history of star formation in ellipticals, therefore their chemical enrichment, is tightly coupled to their structural and dynamical parameters. And that in itself is a very important fact. It really tells us how dynamical and stellar evolution history of galaxies must be connected in a very tight fashion, which is, I would say, still not perfectly well understood. You will recall from our hand-waving derivation of these scaling relations that if you take a Virial theorem, which connects three variables, say radius, mass, and characteristic velocity scale, or radius, density, and characteristic velocity scale, and therefore it implies there is a plane in the parameter space of these three quantities, which we can call virial plane. And then we make some assumptions about homology, that all galaxies are scale versions of each other, and about mass to light ratios, that say you can substitute mass directly for luminosity. That should lead into the observable thing like fundamental plane. Now, any differences in the slope of the observed versus virial plane are telling us something about our assumptions. And in fact, you can show that if you can express mass to light ratio as some power of mass or luminosity and allow for scaling those as roughly 1/5 power, then you can account for the difference in the tilt of the observed plane to the virial theorem. So you can achieve this in various ways. There could be a different mix of dark to luminous matter, as we discussed earlier. There could be different amounts of dark to luminous matter, or there can be different stellar populations. But in any case, they have to be very tightly correlated with the galaxy mass itself. And that is not an obvious thing to arrange. Now that we can measure masses of ellipticals using either virial theorem estimates or, better yet, gravitational lensing, which does not depend on any assumptions of anisotropy and whatnot, we can now form mass equivalent fundamental plane using mass instead of luminosity or mass density instead of luminosity density or surface brightness. And here it is. And it looks very close to the observed one. The slope now is more or less, within the errors, exactly what you expect from virial theorem, which indeed suggests that some assumptions about mass to light ratios and homology are probably what's wrong. You will remember that both Talley-Fisher and fundamental plane have been used as the distance indicator relations, and those are crucial in determining peculiar velocities of galaxies. So the question then is, are those relations universal? Are they the same everywhere in all environment? Because if they reflect different evolutionary histories, say formation of galaxies, evolution in galaxies in a dense cluster may be different than field, then you might expect to see differences in correlations. And it turns out, yes, there are some dependencies. This one is from the study by the SPIDER group, La Barbera et al., that I've shown you earlier. And it shows dependence of the intercept on the projected galaxy density around the galaxy in question, as well as projected slope. And you can see there are small but significant trends. They can measure these only because they had in excess of 10,000 galaxies, so they can put a lot of galaxies in each bin. So the effects are there. We know them, we can measure them, but they're very subtle. Essentially, what these subtle effects say that our assumptions were almost right. Elliptical galaxies do form a very well-regulated family where in mass-to-light ratio changes as a function of luminosity. But at any given mass, there is so little scatter that it's truly amazing. It could be consistent with zero, just measurement errors. So this is an outstanding puzzle that all elliptical galaxies in all environments, everywhere, independent of their size, mass, or anything else, just two numbers determine at least a dozen of fundamental quantities that describe the galaxies, having to do with their masses, densities, kinetic temperatures, luminosities, star formation histories, and so on. Just two numbers. And we can come up with any number of scenarios why this shouldn't be the case. Why, even if you started with pure virial theorem type relation, you're going to scramble it up by different evolutionary paths. And yet, that doesn't happen. Even though processes of galaxy formation are fairly stochastic in terms of random merging and so on, somehow, in the end, galaxies always end up following these correlations. Note also that there are quantities that do not participate in these correlations. Usually those are quantities that describe the shape of the light distribution. So how can this possibly be? Now we can turn to numerical simulations of structure and galaxy formation. And it turns out that if you do this very carefully, you can make synthetic ellipticals in computer. They too follow a fundamental plane, just as observed. There was no new physics put in. There is nothing magical. Same old gravity, dissipation, and so on. And somehow this correlation emerges in the end. We can reproduce this correlation in a computer, but that doesn't mean we understand it. So the tilt is relatively easily understood by changing homology and mass-to-light ratio assumptions. The thickness is not. Why the thickness is so small is truly an outstanding mystery. Same thing for Talley-Fisher relation. So you can look at this in a more general way. You can think of the galaxies as families of objects form two-dimensional sequences in a three-dimensional space, or 10-dimensional space if you want, but at least three. And fundamental plane would be one of them. This is by analogy with stars and HR diagram, which is a parameter space of stellar luminosity and stellar temperature. And there, stars of different families form linear sequences in that space, whether it's main sequence, giant branch, horizontal branch, and so on. So here we have for galaxies two-dimensional sequences in three-dimensional parameter space. So this is just like HR diagram for galaxies. And like we used HR diagram to understand and probe stellar structure and evolution, we can do the same for galaxies in this galaxy parameter space. And finally, let's look at dark halos. Can we look at their scaling relations? At first, this sounds ridiculous, but in fact, we could. This is important because we know already that many Galaxian properties seem to be driven by the properties of their halos because that's where most of the mass is. Now, in numerical simulations, we can see what dark halos look like. We can plot their density profiles, and several have been suggested. One is this one called Navarro, Frank, and White profile, but Sirsic profile works just as well, and just as it describes distribution of light in galaxies, so it seems to describe distribution of dark matter, at least in model galaxies. What about observations? So here is just a set of dark matter density profiles derived from simulations, and the lines going through them are the fit of the Navarro-Frank-White profile. Well, that's the theory. What about the observations? Dark matter is kind of hard to observe, but we can infer something about its distribution from observable things in galaxies, like this is how we do rotation curves. And indeed, with some care and delicacy, Cormedy and Freeman have done this for a whole lot of different galaxies, estimating their central halo densities, their core radii in halo distribution, characteristic radii of halo mass distribution, as well as their effective velocity dispersion, the kinetic energy per unit mass they have to have in order to balance their own self-gravity. And so after doing this, they found out that there are scaling relations for dark halos. And here they are. The quantities like core radii, central density, kinetic energy, they're proportional to some shallow power of galaxy luminosity and therefore galaxy mass. So this is quite remarkable that we can actually measure scaling relations for galaxy halos, which might be actually the root of existence of those that we see for visible light. And that concludes our study of Galaxian properties as such. Next, we will start talking about galaxy evolution and galaxy formation.